Well, it's always a pleasure to be here. This is my third time in about 4 years. So it's nice to be here. Thank you guys for coming back from the break. I'm sure you have a nice lunch. And I will try to entertain you with comments. So I will talk about reactions that actually occur or that we suspect are actually occurrent in comets. Okay? All right. The actual title that I decided to come up with is actually voltage-driven chemistry. And that could involve electrochemistry as also, it could also indicate maybe some plasma chemistry. But in this particular case, I'll be talking mostly about gas surface reactions that are actually driven by voltage or electric fields. All right, so this is the outline of my talk. I have about 37 slides, so you can get a sense of where I am at any given time. And this is what I'll be covering. I'll be talking about charge separation. I'll be talking about electric field, charge separation over here, electric fields, and how they actually move ions, positive and negative. And I'll talk about dust grains. Voltage-driven chemical reactions that we observe. And finally, I give a few examples of type of reactions, radioactive reactions, that we suspect that might be happening. Okay? All right, so let me give you a reminder first of why this topic and what is the context of this topic. So this is some of the anomalies that we observe with the standard sublimation model that has been in place for the last 50+ years. We actually see that each particular comet actually has its own personality. And we know now that it has different features because its composition is different. Okay? The presence of ions and electrons near the nucleus has been shown to be there in a scale that is actually more than would be expected with photoionization. And I'll talk about that. I talked about last time, and I'll sort of mention it again this time. There's this situation where we have what appears to be a lot of outgassing or a lot of volatiles in the, in the coma as a function of heliocentric distance. It doesn't quite match. So you see that there's something else going on. I mentioned it last time, and I'll mention it this time as well. Active jets in the dark side of the nucleus, which are basically not exposed to sun radiation. Sorry. This is something that I talked before. I'm not going to talk it this time, but this is a point to keep in mind. And the origin of comet outbursts is still not clear. I think some of you actually mentioned it and look at it from the electrical perspective as a capacitor. And the presence of a large hydrogen gas cloud is something that I talked last two times, so I will not cover it this time. All right. So I'm going to start here by this work of Rutgers, where he basically proposed a model that can actually explain the rotation of galaxies. And in this model, he actually was brave enough to actually consider the electrostatic force. Okay, so here is basically a figure in this paper, and what he concludes is that at the end of the day, he said that you need to have a charge of about 10 to the 31st coulombs to actually explain the actual rotation on the galaxies that you see. On top of gravity, of course. He says there's gravity, but on top of that, you need to have electrostatic force. This is how much coulombs you need. But he goes beyond that. He says that positive charge is actually located at the center. And what you see, the negative charge will be then at the periphery. So we have a charge separation at this particular case. Now, I will extend this charge separation observed and apply the property of fractality in the universe, okay, which applies to different scales. And I'm going to be also brave to say that we will see this sort of separation of charge, even at the atomic level, when we have a nucleus which is positive charge, and the negative charge is actually an electron cloud actually at the periphery or the surrounding of the nucleus. So I'm beginning to see here what it occurs to me is that there's a fractality here that is occurring. Basically, this distribution is similar at different scales. And so again, being brave again, and I will say that perhaps this is also, and maybe also supported by evidence, that this is how in the solar system we also have charge separation. And I think we've been talking about it, at least in this community, for quite some time, that this is the kind of observation that we see. So I'm going to stay with it. And just note that also there's charge neutrality, but it doesn't really mean that, for instance, at the atomic level, we have ions, positive and negative, so you can also have not necessarily charge neutrality all the time. So maybe you can apply it the reverse way. Maybe at the galactic level, you might have galaxies that would be overly negative charged and overly positive charged. That also happen based on the property of fractality that I'm applying to this observation. Now, here what I have is a cartoonish way, an idealized charge separation that could be occurring at the solar system. So I put the sun here as positive charge, and then the periphery, or at the end of the heliosphere, which is actually a sphere, is not 2 dimensions I have here, will be negative charge. So this is idealized, but most likely what's going to happen, or what's actually happening, just in electrochemistry, is that the charge will actually be not quite as idealized, and this has been shown recently in the last few years when we talk about double layers, but I'm not doing it this time. But the charge will be a little bit intermingled. So what we really want to look at is at the net charge. Where is the net charge? Where is the net positive charge? Where is the net negative charge? And I would just want to highlight here is that we know, for instance, that the substructure of, you call it magnetic field, I like to call it electric fields because it's easy for me to understand. The solar system level is not homogeneous. It's actually quite complex. And I base these comments on the observation that comets behave quite differently. You could have the same comet on the same route, and it will actually not follow the same behavior, right? So that means that the electric fields that are, or the voltage differential that are being experienced by the comet along its path, it's not the same every time. So I think Dr. Scott mentioned magnetic flux ropes, which to me as electric fields. And these electric fields are dynamic, okay? So that's part of the substructure that I see. And what I want to highlight is that if this model is correct, and I think I'm mentioning this for the 3rd time, if this model is correct, what we should be able to see is that the net motion, okay, of positive and negative ions should be such that the positive ions will go from the sun in a radial form upwards in this form. So you see all the positive ions, either helium, plus, protons, and so on and so forth, or even heavy metals. They should actually have a tendency to move to the periphery or the heliosphere, because that's what the negative charge is. So it would be a natural tendency for these particles to move in that direction. Now, allow happening in between. Allow happening in between. So it's not a simple model, but the net charge should be in that direction, right? And when you have positive charges moving in one direction, the negative charges would like to follow, especially electrons, which are faster because they're not as heavy. They will also intermingle. But you can also have, of course, electrons move along with the positive ions in the same direction as well. But the net charge should be the opposite. So net charge, I should be able to see electrons going or moving towards the sun. I would like to see that. So this model should say that this is what's happening. It's not clear at this stage. We know, for instance, the positive ions definitely move radially away from the sun towards the periphery of the heliosphere. Okay. Now, how will a voltage profile will look like based on the model that I just sort of mentioned here? Well, this is a diagram that I have on the left, radially concentric circles that specify distance, and on the right here, what I have here is a graph of voltage versus distance. So how will it look like? So if I just simply look at the positive or close to the sun, or even on the surface of the sun, my voltage would be arbitrarily positive. And then as I see the distance, I see this as a function of distance, my voltage will drop. Okay? So I draw this by my hand, and I think it's probably okay, because this voltage drop is a gradual voltage drop, or it should be a gradual voltage drop, and it's going to be, not going to be beautiful, okay? It's not going to be nicely exponentially or polynomial. It's going to be up and down. And so I expect this diagram, this picture here, this cartoon is probably okay. And then when we go all the way to the periphery of the heliosphere, well, it would have a more stable voltage differential. Now, when I look at this voltage differential here, then I don't need to have, just because of separation of charge, I don't need to have any motor or EMF force or anything to explain the motion of ions. Electrons, I mean, I have a voltage differential here, and electrons will move towards the positive end, and ions will move towards the negative end. So the electrochemical concept of motion of ions is just as that. But what I cannot really explain is the charge separation. So I would need the engineers and so on to actually explain why there is such separation at the level of the universe, galaxy, solar system, atomic level. Okay, that's something that I can explain. Now, let's take a look at the comet. So I've been talking about the solar system. So this is the sun, flat environment in the periphery, or the end of the heliosphere. If I look at the, if I think of a comet as being an electrode, so I go back to electrochemistry and say, I think of the comet as being a negative charge electrode, okay, in a plasma environment that is both negative and positive charge depending on location or heliocentric distance from the sun. Then the profile will look like this. So this is the voltage profile over here. We have voltage, we have distance, and in this model, I have the center. The center here is negative charge. That would be my Comet 67P or any other comet. And because this is an electrochemical model, then I will have a layer of positive ions, and then we'll have a layer of negative ions. So the profile basically will look like this. Okay, there will be a voltage drop from the surface to the plasma environment of the comet. In this case, it's shown as a radical drop. Okay, it doesn't have to be that way, but this is how it's shown in this diagram. And there will be another gradual voltage drop at the end as we extend far away from the nucleus. Okay, so again, there's a voltage involved. There will be electric fields present. This is a non-zero electric field, and that would be enough to provide energy required for ions to move about, collide, and give rise to chemical reactions. All right, so that's the end of the first part. Basically talk about how such separations leads to electric fields. Now I'm gonna go and talk about how the electric fields has been shown to provide the energy required for ions to, well, move about. Okay, so what I'm gonna do here is just give you a few examples of studies that have already been done. Okay, and in this particular example here, what I have is a graph that shows me here spectral density, magnetic field, and here is the frequency of this magnetic field, which shows that it's between approximately 2 nanotesla to approximately 4 nanotesla. I think we're talking about the solar system, solar flux here. And this magnetic field shows all different kind of oscillations, but in this particular case, it shows a frequency of 40 millihertz, which is a little bit different from anything that's been discovered before. This corresponds to 67P. And basically what it shows is that there's an electric field in the order of 5 nanoamps per centimeter square, okay, close to the nucleus. Another example here, where I have what is supposed to be ion flux versus distance from the sun, okay? And what it shows in this particular study is that what is assumed to be water ions, okay? So actually, in this particular paper, what it shows is that, based on the technique used, is that you're able to detect the ions the velocity that they come in, actually the speed as well, direction. But they don't really know what kind of ion it is. So they refer to another study that says that, okay, around the nucleus of Comet 67P, we have a large number of ions that appear to be water based on spectroscopic data. So based on this interrelation, which is, I think is okay, it's fair, academically, it's fair. But it doesn't really mean that it's water ions that are there, okay? But it's possible. So I'm not gonna say it's not water ions, but I'm just gonna give you a reminder that how the conclusion came about, okay? It could be something else. It could be other volatiles. There's a lot of volatiles around 67P that are also there. So the important thing is that these ions do have velocity, okay? And where do the kinetic energy come from? Especially since in the vacuum space, we're talking about very low temperatures, okay? So kinetically speaking, well, they need to have energy coming from somewhere. And so it's the electric fields that provide the energy. The energy is given here. There are two types that we can see here. The cold water ions, 10 to 50 electron volts, and hot ions, accelerated water ions, 120 to 5,000 electron volts. This is a tremendous amount of energy in terms, I mean, at least from the chemical perspective that we're talking about here. Just to give you a background or context, if I want to ionize hydrogen, atomic hydrogen atom, I just only need 13.1 with 13.2 electron volts, maybe a little bit more, let's say 14 electron volts. So you'll be talking about a very large amount of energy, okay? In my opinion, this is good enough already to actually strip out electrons from the surface of the nucleus, provided the electric field is being experienced on the surface of the nucleus, of course, right? Now, what was discovered here, this is very interesting, is that when you look at the distance, this part here, when we go from 3.6 to 2 astronomical units distance of the Comet 67P from the sun, okay? What's called the water ion flux. So in the terminology that's being used in the standard model, it's always outgassing, because it's always the gas coming out from the nucleus, which is not clear. It's definitely not clear anymore, okay? It increases, right? So the number of volatiles increases. But as a function of solar flux, okay, it indicates there is not a linear relationship. And the expectation could be is that you increase the solar flux, you'll be able to see more sublimation, and therefore you're going to have a great amount of volatiles. Well, it's definitely not linear, and in my opinion, there's other factors involving here, okay? And I'll mention that in other slides, of what I think is happening here. So here's another example of, again, electron, in this case, it's electrons, not positive ions, that have been detected in the coma. They've also been detected near the nucleus. And these electrons also are what's called superthermal or hyperthermal, which means that they have a lot of kinetic energy. We're talking about hundreds, a few thousands electron volts of energy of these electrons. So all this energy is being supplied by electric fields. This is a very old, actually, slide. I think I used it last time. And just to highlight here that at the time, we were talking about maybe 100, a flux of 100 per volume, 100 electrons per volume. But this number has changed now, maybe to 1,000, maybe to 10,000 per volume, okay? And I just want to highlight, look at this potential here. It's 100 volts potential difference observed in the vicinity of the nucleus of 67P. So it's a large. This is a lot. I don't know. From a chemical perspective, it's a lot of energy. It's a lot of energy. All right. And so again, in the previous slide, we use an electron sensor and for an ion sensor to detect directly. So I really like that. We're actually sensing these ions. And in this case, we are presenting a work that actually uses UV emission spectroscopy. It's a different technique. And I really like the fact that you have different techniques collaborating the same phenomena. This is something that we do here on planet Earth frequently. It's very difficult to do this in space because of limitations of instruments and because of just massive scale of distance. But with the Rosetta probe, we're able to see different instruments collaborate similar phenomena. But it's not beautiful. Data should be that way. Data is not beautiful. It's nasty sometimes. I've seen an example, for instance, where you have different techniques, look at the same phenomena, and the numbers that they come out with is totally different, off by 20%, okay? But that's fine. That's how it should be, okay? We need to have more population sampling before we can actually reach conclusions more solidly. Right now, I think we're on the weak end. Now, this is a different work, and you can actually see the citations over here. And I want to highlight, I want you to bring out this highlight here in yellow, okay? Because 67P, it was determined not to be a very active comet, okay? But when you are at a distance of about 3.6 astronomical units, okay? This comet already show, okay, a lot of activity, electrical activity, a lot, okay? And this goes again against the idea that everything occurs because of sublimation. Sublimation is usually thought not to be active after 3 astronomical units. But in here, we're talking about 3.6, okay? So it's way beyond the sublimation level. But you still really see a lot of ions and being active around the nucleus. So something else is happening. And what I really suspect is happening is that this is actually electrical activity. I think I mentioned back in 2013 when I really did not know that much about comets. But I suspected that, I said that if we really want to differentiate between sublimation and electrical activity, we need to go far away from the sun, where sublimation is not effective. We need to remove that variable. And I think this is a particular example where that variable has been mostly removed, and we still see a lot of activity. And I think this is a very important work that just came out this year. What we have here is an example, actually a very good work, but it's an example of a Langmuir probe. So what we're actually showing you is IV characteristics. For those of you who don't know what it is, I mean, this is current, and here would be voltage. Okay, so it's an IV current voltage curve. And in this particular example, what it was done is that the Rosetta probe had actually 2 probes extending out a particular distance from each other, and a voltage was applied between these 2 probes in reference to the Rosetta instrument, and then the current was measured between the 2 probes. Okay, it's called a Langmuir probe. Some of you might be familiar with it, and we see here as a function of heliocentric distance, basically how far away the comet was from the sun, and also as a function of cometal distance, how far was the actual Rosetta probe from the comet. So in this particular example over here, where we only see a few nanoamps of current, okay, especially positive bias, what we see is that this corresponds to the solar wind because we're actually 7,000 kilometers away from the actual comet. So the solar wind shows currents in the nanoamp range, okay? If we move a little bit closer in terms of distance from the sun and much, much closer to the actual comet, we see that this current actually increases from 5 to all the way to 20 plus nanoamps. If we, again, move a little bit closer, 2.757 astronomical units, and still close, still within the comma of 67P, we see a much larger increase, about 100 nanoamps. And we're very close to perihelion, even though we are far away, relatively speaking, to 35 and 28 kilometers. we see a current of about 15 microamps. So we see a quite large increment of current. All this means is that you have a lot of electrons and a lot of positive ions. But in this case, I guess we are measuring only electrons, but you're going to have both in the vicinity of the nucleus. Okay. So there's plenty of energy for these electrons. There's plenty of ions and electrons in the vicinity. This always is going to lead to collisions. Okay? And before I go to talk about chemical collisions, let me also mention the fact that I've been talking about positive ions and I've been also talking about electrons, but there also was this nanograins called clusters that are actually present. So in 67P, we have, here we have grain energy in electron volts, and here we have size. And I'm going to concentrate on two types. You can see these columns over here. This one, for instance, is about 50 nanometers, and you can actually see that it will have this much energy. So we're talking about 10 to the fourth electron volts, so 10,000 maybe. There's a lot of energy involved, which involved with these clusters. So if we go a little smaller size, about 5 nanometers, we see that we're talking about a few hundred electron volts energy. So nanoclusters are also present. Now, like I mentioned to you, they range from 500 to 10,000 electron volts for approximately 50 nanometers, and from 1 to 200 for 5 nanometers. Okay? Now, in this work, they have Rosetta within a particular distance. I don't recall exactly, but it was not far from the nucleus, and they placed or oriented the probe towards the nucleus, and they begin to measure both positive and negative ions. And what they realized is that they couldn't detect any positive ions. They only detected negative ions. So, to me, what it indicates, they basically argue that it's just an instrumental error, which it could be. But what it indicates to me is that it gives me an indication of what is the substructure of the electric fields around the vicinity of 67P. You need to be careful with orientation, okay? If you're thinking about the nucleus, which is negative charge, I would suspect the negative charge ion electrons would be actually moving away radially from the nucleus of 67P. So it such makes sense to me that you will read them, you expect them to sense them. But the positive ion, the net charge, the net motion on them should be in the other direction. And that's what we see a lot of protons in heavy metal ions, helium, alpha particles. They're all moving towards the nucleus, and actually they collide on the surface, and they create a lot of sputtering, right? So orientation is important. And again, this corroborates the fact that, or maybe the observation that the electrons come out of the nucleus, and the positive ions should be moving towards the nucleus. Now, I'm going to move a little bit to Lovejoy, because I don't have enough data with 67P, and what I want to highlight here is that most of these clusters, which actually show a lot of striation behavior. Okay, this is also 767P, but the analysis of what this striation behavior or these particles are is not clear. Most of these actually is metal ions. Metal ions with low ionization potential. Okay, they're easy to remove electrons from, and because you have this voltage difference, this applied voltage around the vicinity, which I think is dynamic. You will see these minerals being removed from the surface. Basically, electrons are being stripped out. And then you will have this left out of it. You basically destroy the structure, the lattice structure of the minerals. Electrons go in one direction. You have the positive ions going in the other direction. And what is very interesting is that because of the size of these clusters, we cannot attribute that to solar pressure because they're large. It's definitely, but they're actually in motion. They're actually being accelerated towards solar wind speeds. So they go from a few electron volts or a few miles per second velocities to about 300 to 250 I think it's meters per second, excuse me, meters per second, which is the solar wind speed. So they're being accelerated by electric fields, right? The electric fields are present now. And again, I use that as evidence of the electrostripping model that I presented last time. And to me, that model actually explains why we see a lot of electrons, which are due to this model and not to photoionization. Because there are many works that have been talked about there, indicates that there's more electrons that should be allowed by photoionization. Well, we have electrostripping here behavior. And this is being observed with all the other comets as well. All right, so let me move to something more interesting, as voltage-driven chemical reactions. So I set up the table. So I show you, for instance, that we have charge separation, we have electric fields, which are present, which are accelerating electrons, and positive charge. So what do they do? Well, I mean, what happens when we have all this together? Well, what's going to happen is you're going to have collisions. So let me briefly show you what a model or what kind of collision it is that you're going to have. Well, you're going to have either gas-gas collisions or you're going to have gas-surface collisions. And that's what we see. So I want to talk about gas-surface collisions, and now I'm not going to talk about gas-gas. Because gas-gas collisions will occur in the coma, okay? But the gas-surface collisions will occur also in the coma, but in the dust grains and on the surface of the comet. And I think that's more interesting. So in this particular model, what we see is that the rate constant, which is associated with a reaction cross-section. What do I mean by reaction cross-section? I don't know if you guys can see here, but here we have a cylinder which explains this particle which is in motion, and what we will do if it moves in this direction, provided that you have all the particles in the vicinity. Well, they will react. There will be a reaction. So this is what we call the cross-section. This is the cross-sectional area. Okay, and the kinetic, we basically talk about the speed of reaction is being controlled by this cross-section. Now, for the reactions to occur, or for a bond to form, okay, you need to have the right energy, and you need to also have the right orientation. But I guess what I want to highlight in this slide here is that the kinetics also follow what is called the Maxwell-Boltzmann distribution, which is shown in this graphic over here, where I have the number of particles as a function of kinetic energy, and only the particles which are at this end here have enough kinetic energy for them to collide, which will lead to potentially a chemical bond. Okay? If they don't have enough energy, then nothing's going to happen. They just bounce off. Okay? And you can see that it's a function of temperature. If you increase the temperature, you also increase the amount of particles available for collision. Okay? And there's a barrier, which we call the activation energy. Okay? So this is based on temperature. Okay? And I show you here is, like I said, the kinetics are based on temperature. This is KT. It refers to K is the Boltzmann constant, and T is temperature in kelvins. So you can see here, you also hear here, so it's connected. Okay? Now, one of the biggest, I'll say, challenges for chemists, okay, astrochemists, has been the fact that you see a lot of chemicals, a lot of volatiles, a lot of reactions occurring not only in comets but also in space, and they cannot really explain it because the temperature is not high enough. All right, just not high enough. So, if you only look about the temperature model, okay. And what I mean by temperature is only given by, say, solar radiation, like UV light, right? Photons with enough energy. Or I cannot think of anything else in space that can actually provide energy. So if you're far away from stars, for instance, well, you don't have a source of energy, so the temperature is low. But you see chemical reaction. So what's happening here? Okay? And this is why I wanted to mention to you guys that you need to have the right angle. If you don't have the right angle, there's no reaction. Well, there's a problem here, okay? But this can be solved because I just showed you that we have a lot of superthermal electrons. So the energy required for collisions to occur is actually being given out or provided or granted, as you want to call it, by the electric fields, okay? Which is due to charge separation. So electric fields give the kinetic energy necessary for ions and electrons to react. And they accelerate, obviously, both positive and negative particles. We also have surfaces, okay, in comets, silicates, metallic, organic surfaces that are allowed there, which provide or can catalyze these reactions, okay? And this is not temperature dependent, definitely not temperature dependent. So forget about temperature, forget about the fact that you're in a cold area of space. You can still have reactions as long as you have electric fields, okay? So we still apply collision theory because the particles have kinetic energy, but it's given by electric fields, not solar radiation. Okay, so this allows us to do chemistry and not to worry about temperature. And I think that's a very powerful situation. And I'm going to end up my talk by talking about one particular type of reaction. It's an Early-Rayleigh reaction. This is a gas surface reaction. I will talk about two cases. And just to remind you that we have particles, those particles in the comma 67P, all different sizes. So reactions can occur, definitely can occur over there, as they can also occur on the surface. All right, so conditions necessary for this particular reaction, which we're talking about the formation of deuterium. Deuterium is a compound, basically water, it's called, but it just have one of the hydrogen actually has a neutron, so it's a behavior. We have, again, from the previous work, we have water ions, okay, accelerated at between 120 to 100 electron volts, and we also have what's called core ions between 10 and 50 electron volts. So these are available. Potentially a reservoir or deuterium. This is not corroborated. This is just a supposition, okay? It's not really clear that the minerals on Comet 67P are rich in deuterium, okay? But this work was done in the lab, okay? But we do have, for instance, that some deuterium rich in soluble organic matter is being shown to be available in comets, but not 67P. But you need to have these requirements, which are potentially available in Comet 67P, to show that the Comet 67P has a ratio corresponding to this. This is a deuterium to hydrogen ratio, 5.3 plus or minus 0.7, 10 to the minus 4. Okay, this is extracted from deuterium, how to call this, outgassing versus water outgassing. But I can also say deuterium formation versus water formation, because it's not clear if these two species are actually outgassing or being formed in situ. So you take water, you take deuterium, and you get a comparison. If you want to look at it in terms of something that makes more sense, we're talking about liters per second of being formed. Deuterium, about 12 liters per second versus 17.7 thousand liters per second of water that's being formed per second. Okay? These numbers are being extracted based on spectroscopy data. Now, in this particular model, and let me bore you here a little bit with chemistry here, but it's actually simple. We have a surface, which is rich in deuterium, and you can see the deuterium right here. Okay, so that represents this grain that I talked to you about. And if you have water ions with the correct energy, then it will form a complex shown over here. Okay? And this complex, which is an intermediate species, then separates into a deuterium ion and another hydrogen negative charge ion here. Okay? Now, this is something I already mentioned. Now, this can happen. Okay? So it's shown to happen in the lab. It's shown to happen in the lab. Okay? And this is the graph, or the image to prove it, the graph. We have extra energy. This is how much energy is being bounced off from the nucleus. And here what I have is the incident energy of the incoming ion. So let me see what it is. You have a surface, which is made of platinum, which has been dosed with deuterium. So you have a surface with a lot of deuterium. And here I have a gun that projects water ions. And I'm hitting the surface with water ions. All sorts of stuff happening. All the different volatiles go to a mass spectrometer, so I know what they are. And so here is a graph that shows different species that form, okay, all different species that form. And the one that we actually looking at, they're interested in, would be the one in red, which is somewhere over here. Okay? So all these species different actually form in the lab. Okay? And so you make the assumption that, okay, if the conditions are given in the lab, and if you look at the comet also has similar conditions, it can happen. Doesn't mean they're happening. It can happen. All right? But I like this approach, even though you'll see that there's a limitation here. But I like it because it is lab work. It can be repeated. Okay? It can be repeated. Now, I'm almost at the end here of my talk. This is another example. This is for molecular oxygen. It follows a similar idea. You have a surface here, but this surface now is reaching oxygen. Now, that we know. Right? We know silicates will have hydroxy groups on the surface. We also disallow oxides, so that we know is correct for C7P and for allow all the comets. And so we have incoming water ion again, interacts, okay, with the surface, extracts the oxygen, okay, and eventually you get a subsequent reaction that gives you molecular oxygen. Okay, this is a little more difficult for me to understand. Okay, but it can happen. All right, and again, what I really like about this is that the conditions are there in Comet 67P. It's happening in the lab. Okay, we know that the water cut ions have enough energy. Because this, given by the electric field, so this can happen. All right. This can definitely happen. And here's the evidence shown. Again, this is the energy of the incoming particles that are being detected by mass spectrometer. Here is the amount of energy you put in the particle hitting the surface. Again, the surface in this case is platinum with oxygen. So as you can see in the lab, this is idealized. This is not how I suspect it is happening in space, but this is idealized, but it's a good start, okay? It's a good start. And we actually see molecular oxygen, which is in black, actually being formed, okay? And you can see there's a linear connection between the amount of energy that the incoming ion will have and the energy that it will come out, okay? So it's a very interesting situation. But there are limitations for this model, okay? So I just show you, okay, you can have reactions in there, the conditions are there, but there's something that is contradicting here. So this is a piece, a paragraph from the authors. And you actually see here, for instance, it says the water ions in the extended coma are accelerated towards the nucleus. Yeah, we know that. Okay, and the crust is actually dehydrated. So where are the water molecules coming from? So I really don't understand that part. Okay, because okay, I mean we're all trying to figure out what's happening. But I think it's best to start explaining where the water ion is coming from first, okay? And then once you understand where the water ion is coming from, okay, you can say, yeah, we have plenty of them, and then we can actually, say that they're actually hitting the surface or hitting the surface of the nucleus or hitting the surface of the different dust grains, and these reactions are occurring. So there are limitations to this model. I would suspect that the water molecules first needs to be explained, and they can do it. And there are many labs that can actually do this, and I hope that they can go forward and do it. I do not have the equipment to do it myself. I don't have high vacuum equipment to do it. And I'm going to end up by giving you an illustration on not only the model, but actually scientific limitations. Okay? So there's this work done on Lovejoy, this using infrared spectroscopy. Okay? And look, and let me show you this. So here's Lovejoy, okay? He is pre-perihelion, and pre-perihelion, the experiment was done using radio waves, okay? Post-perihelion, the experiment, post-perihelion, was done using infrared spectroscopy, two very different techniques, okay? And so I'm in, it's difficult for me to look at this data because I have here production rates for deuterium, production rate for water, and then I'm looking at the ratio over here, and this is how much it is versus the Vienna standard mean ocean water. Basically, if you look at the ocean on Earth, this is the ratio that you will see between deuterium to water, 0.89. Okay? Now, if you look at the infrared data, I see different production rates, but I'm going to concentrate only on the Vienna standard mean ocean water, deuterium to water ratio. Very different. So 0.89, 1.94. The authors went on and talked about this. They had a whole publication about this. Now, these guys are actually very honest, and they explain that how can we do this? I mean, this is one technique. To me, this is apples and this is oranges. If you want to do a comparison of pre-perihelion, post-perihelion, we need to fill the gaps over here. We don't. And I think this is what's happening when we allow the data that we see for either astronomy, cosmology, for instance. There's not enough, at least from my perspective, as I'm training as an analytical chemist, so I'm training at looking at data, and I need to have different instruments looking at the same thing. If they agree, okay, then I'm satisfied. But I don't see that much happening in these fields. Besides the Rosetta, and when I look at Rosetta, I mean, I read maybe like 50 papers. They all concentrate on their own little field, small little field. And so I think that's the biggest problem that we see, is that we, at least for astronomy and cosmology, we just don't have enough. There's not enough data out there for us to begin to see the bigger picture. And so this is just to show you, okay, look at the spread of the DH-water ratio. When you look at statistically at all the different reports, this is how it looks like. Okay, it's quite, to me, it's incomplete. We need more data. We need more sample population to actually come up with a conclusion. So to finish up, take home points here. Electric fields are present in the vicinity of Comet 67P. These are used to provide kinetic energy for ions and electrons. And I gave you an example of gas surface reaction. In the previous talk, I talked about actually plasma reactions, coronal discharge, which again can occur because you have electric fields. And I'm just going to end out here saying that current methodology and instrumentation is lacking, it's insufficient. We don't have enough. Well, thank you for your attention. This is all I have to say today.